So to begin with, we're going to be learning about electrical resistance itself. We're going to learn about what resistance is, what causes it, and what changes it. Now, as we know, electric current is the rate of flow, or the rate of change, of electric charge. Current equals change in charge over change in time. Now, a voltage between 2 points in a wire will cause current to flow in that wire. The reason for this is because it makes the electrons inside the wire move. So how does the magnitude of the current vary with the magnitude of the voltage? Do you think that a bigger voltage will produce a bigger current, perhaps? Well, yes, it will. But how will the current increase? Well, it increases the square of the voltage, or linearly, or the square root of the voltage. Well, it turns out that the current through a conductor will increase linearly with the voltage across it. That means that as we increase the voltage, the current tends to increase at the same rate. The constant of proportionality, that is, the slope of this graph, the number of amps per volt, is dependent on the conductor. So without knowing the conductor, we can't predict the slope of the graph beforehand. We call the slope of the graph the resistance of the conductor. So the resistance will tell us how many amps we get per volt. Now, a conductor's resistance is a measure of how much it resists the flow of electric current. So if it has a very high resistance, we'll get a very low number of amps per volt. We represent resistance with a capital letter R. Capital so that we don't confuse it with a lowercase r, which might mean something like radius. We measure it in a new unit that we're going to call the ohm, represented by the Greek letter capital omega. It's named, of course, after this fellow here, George Ohm. He was a German physicist born in 1789, which is, of course, quite some time ago now. The relationship between voltage and current discovered by Ohm is represented by Ohm's Law. Simply stated, its current increases linearly with voltage. Fair enough, right? We can write this mathematically as well. Algebraically, the law is V, voltage, equals IR, current times resistance. So with a very high resistance, the same voltage will produce a lower current. And with a very low resistance, the same voltage will produce a high current. Now, if a substance has a very high resistance, very little current will flow through it, right? No matter how high the voltage is. Obviously, the current will increase with voltage, but if it only goes from 1 milliamp to 2 milliamps, when we move from 10 volts to 20 volts, then it has a very large resistance. Conversely, if we apply exactly the same voltage to something that has a very low resistance, then we get a much larger current. V equals IR, so if V is constant, but R is much lower, then I must be much higher, right? Now, an example of something with a very low resistance is copper wire. Copper is in fact a metal with lower resistivity than most other metals. We can see a piece of copper wire in the middle of this picture. A block of wood, like the sticks in this picture, have very, very high resistance, and this is what makes them insulators. Now, the exact resistance of each of these will depend not just on what it's made out of, but also on its shape. As we'll see later, conductors with different shapes will have different resistances, even if they're made of the same material. So that's the end of the theory. We've learned about resistance and how it relates voltage to current. Let's go on to some questions.